Good afternoon, everybody. Welcome in this last session in a set of 5 around energy cost reduction. Today is a session on optimal setting of your drives. Prior to the start of this session, I'd like to remind you all that your cameras and microphones are muted by default during the presentation, and that any questions can be posted in the Q&A chat box. They will be answered at the end of the session during the Q&A, moderated by one of our staff. We will also record this event and share it at a later moment. So please do not record it yourself. That's not allowed. You can see it on the Flanders Make website. Now, prior to us starting, I'd like to present myself, my colleague. I am Jeroen Stuits, Core Lab Manager of Motions, the Motions Core Lab in Flanders Make. I have a background of energy engineering, hence my attendance today. And I'm supported by my colleague Kurt Stockman from the University of Ghent, professor there at the campus in Kortrijk, and the both of us will be presenting this session for you today. So without further ado, let's dive into the contents. The topic is optimal setting of your drives, one or multiple. So let's first understand what that content is. If we look at the figure to the right, it's a familiar sight for many, I guess, a large electrical motor controlling a certain application. And if we draw it schematically, as you can see in the bottom, typically the electrical grid is used as a source of power. That power is distributed to a certain power converter, which supplies a motor of energy, and that motor drives a load. And typically you're most interested in the load because that's where your application would be connected. Energy flows from left to right or potentially back again through regenerative braking. And the drive, the content of this presentation, is the combination of the power conversion, typically using power electronics, and the motor. And roughly 2/3 of industry's energy consumption today is consumed by these electric drives. Even more, 75% of the applications of those drives are pumps, fans, or compressor systems, so are typically non-dynamic loads. And those are the purpose of today's presentation. And there have been lots of publications and lots of topics on how to reduce energy consumption with these drives. So to list the most important ones, first of all, in such an overall system, you can of course use more energy efficient motors. Today, the standard is IE3, but the IE4 motors are available today. And if you come from very inefficient motors and you move all the way to very efficient motors, you can save around 10% in energy. But of course, it requires a certain investment because you need to replace your motors. An alternative step, which is often presented, is to move from fixed speed to a speed controlled application, depending, of course, if it's relevant for you. But if you can speed control your final application, and you can do that through the motor, that's typically much more efficient, and the energy saving potential there is up to 30%. But again, requires an investment because your motor is no longer directly connected through the electrical grid, but needs a converter and needs control. But the most important thing to be done in such an overall system is to optimize the overall system. That is to use the knowledge of your load in the design and control of your power conversions and motors. And by optimally doing that, you can save up to 60%. And depending on the conditions, of course, the required investment can be significantly higher. An example of such an overall optimization is to optimally control a pump for the flow that is required, for example. So those are well-known improvements, but there are other energy saving potentials out there, such as optimizing your power distribution. It's a recent result from Flanders Make, where the energy saving potential is up to 10%, but of course it requires again an investment to redo your power distribution. And then the final set, which is the saving we're going to discuss today, and that says you can also optimally set control parameters parameters of your drive system. And in essence, those don't require any investment because it's a parameter tuning. Everything is already there. It requires some time, of course. And as a consequence, the energy saving potential is slightly less. But depending on the settings applied today, we've found that you can calculate or you can save up to 5% additional energy. And it's the latter that is the purpose of today's presentation, the optimal setting of your drives. And the settings with the most energy saving potential will be handled by my colleague Kurt.
Thank you, Jeroen. Good afternoon, everybody. So indeed, let's take a look on how we can optimize the inverter motor system in an application which does not require any high dynamics. By the way, for those high dynamic applications, we had a session about 3 weeks ago on trajectory optimization, and I think that at the end of this presentation, you will see the link where you can find that recording of the session on trajectory optimization. Now let me start with a graph. You see here a graph in which we see the efficiency of a speed-controlled motor at rated speed versus the efficiency of that same motor without variable speed inverter. So the blue line, as you can see, is a directly connected motor to the grid. And if we add a power electronic inverter, we end up with a green line, which shows you that using a speed control costs us 3% approximately in efficiency. So the first question we should ask ourselves, do we really need variable speed in our process? If not, then the first and an easy way to save money is to get rid of your variable speed drive. It happens typically that some starting conditions are critical and the variable speed drive is used for that, but once in operation, then if it's not longer necessary, we don't use it. Of course, in the remainder of this presentation, we will use a variable speed drive and look into 3 parameters that can be optimized: flux control, the switching frequency, and the adaptation of the DC bus voltage in the case that you have an active front end. Yeah. Now, Jeroen already mentioned that we have several machine technologies. I've shown here 2 graphs. The top right one is the efficiency map of a permanent magnet IE4 11 kilowatt machine. It has a high efficiency up to 94%, and what you should see here is that also in part load operation at lower speed and torques, that efficiency remains quite high. That's because that permanent magnet machine brings magnetizing because of the magnets that are in there. Of course, those magnets cost you something, so the purchase cost of such a machine is quite high. Traditionally, in a lot of applications in industry, we still use the induction machine. If we compare the efficiency map of the induction machine with that one of a permanent magnet machine, we end up with the efficiency contour difference that we see in the bottom right. And what you see there is the less performance operation of an induction motor compared to a permanent magnet machine in part load operation. So ranging from 50% of speed below that and torques below 50–60%, you see that we lose quite some efficiency. That's because, of course, the induction motor always needs a magnetizing current, which contributes to the joule losses of that machine. Another recent machine is a synchronous reluctance motor. It has better efficiency typically compared to an induction machine because it has no rotor joule losses, but it does require also a magnetizing current. So some of the parameter settings that we will discuss later on could also be used for that synchronous reluctance machine. So in the remainder, let's focus on that induction machine, the workhorse in industry, and see what we can do. So, as I mentioned, if you vary your speed and torque and you work in part load operation, then you don't always need the normal or rated flux in your induction machine. So what you can do, of course, is to reduce that flux. And if you do so, you can see that the torque speed curve that you see in the right top figure, it drops. It's not a problem for your application because you still produce the required torque at a given speed for your application. But the result, of course, is that the magnetizing losses in your machine reduce together with the stator joule losses. That's, of course, is beneficial for the efficiency. For a 4 kilowatt IE4 motor, you can see the efficiency contour when applying flux optimization. And what you see are the savings compared to a same machine without the flux optimization. And in part load, we have gains of several percentages that are possible. Now, how should you do that? Well, commercial applications, commercial drives do contain parameters for automatic flux optimization. They work fine, but it's our experience that they are rather conservative. If you adjust that flux manually, you can do a little bit better. Now, why are commercial drives rather conservative? Because the disadvantage of reduction of the flux is a reduction of your torque dynamics. If you reduce the flux, you don't have the rated torque of the machine, so quick accelerations are not immediately possible. But if you really want to optimize, a manual adjustment of the flux gives you the best results. How many savings can we attend? Well, typically 2 to 6%, but in a few slides I'll show you a case study with some concrete numbers. The second parameter which we should consider is the switching frequency of the IGBTs in the variable speed drive. Typically, you can change that switching frequency between 1 and 16 kilohertz. It depends a little bit on the size of your drive. For higher power ratings, don't get up to 16 kilohertz, but you still have a playing field between 1 and several kilohertz. Now, what's happening here? Well, it's a twofold story. You see two graphs. The top graph shows us the inverter losses. Each time an IGBT has to switch, we get some power losses in that component. And you can see that the total losses raise with the switching frequency. So from the point of view of the inverter, well, we would like to have a low switching frequency. If we look to the motor, well, the motor expects some kind of sinusoidal current, and we have to make it by producing a PWM voltage waveform. But yeah, it's clear that the higher the switching frequency becomes, the more sinusoidal your current will be. And the illustration you see is not that sinusoidal. Now, it's only the fundamental current component that really contributes to the torque producing. So all harmonics result in additional heating of your motor, which is a loss of efficiency. So the motor, well, he wants a higher switching frequency. So we have to make a compromise. Well, literature and also measurements in our labs have shown that 4 kilohertz is a very good practice, and potential savings up to 1% are possible by adapting that switching frequency. The third parameter is the adaptation of the DC bus voltage. Of course, to do so, you have to have a drive with an active front end. So you change your diode rectifier with an active front end, which allows you to regenerate energy to the grid or to optimize the power quality of the current you draw. Now, if you have such an active front end, you do have the possibility to change your DC bus voltage. Some measurements were done at Flanders Make with a variation of the DC bus voltage between 575 and 730 volts DC. And what did we expect? Well, we were looking into the efficiency of a small motor, and two things happen here. First of all, if you increase the voltage for the same power, you would expect the current, of course, to drop. So you could think that the conduction losses will also be reduced. On the other hand, if you have higher voltage in your DC, then the voltage variation during switching is bigger, the VDT, which results in more switching losses. So also here we have to be careful, because a compromise will depend on the power rating of your machine. For the given graphs, for a small motor, we see that in that case, a increase of the DC bus voltage was not so good. So we had a reduction of the efficiency as the DC bus voltage was increased. And for that specific machine, we had potential savings up to 5%. Now let's take a look at the case study. The case study it's a gearbox test bench. So a gearbox is loaded with 2 induction motors of 150 kilowatts. You can see them in the red dots in the figure. Both of those induction motors are speed controlled. So one is driving the load motor, the other one is regenerating energy to load the gearbox. And both drives are DC bus coupled. They don't have an active front end, so it's a diode rectifier, and the energy is transferred between the drives. Now we measure the electrical energy at the entrance of the grid, which is actually the losses in the entire system that we measure. That test bench is also not always operated at full capacity, so we also have part load operation here. So we will look into flux optimization and results of the switching frequency. Let's start with the switching frequency. You see a table at the bottom of the figure. And when we started the measurements, we saw that the factory settings of those switching frequencies was 2 kilohertz. And we measured the power loss of 37.3 kilowatt. So we gradually increase the switching frequency, and you see if one of them had a 4 kilohertz switching frequency, we had a little increase or reduction of the required energy. And the best option was to have both drives at 4 kilohertz. And there we had a reduction of the losses with 2.4% by just adapting one parameter in the drives. We also tried to go higher. You see that we also tried 8 kilohertz and 2 kilohertz, but then of course the losses in the IGBTs become too big, and there's some safety measure and error to protect the IGBTs, so that was not possible. So here we can see that at 4 kilohertz indeed is also for higher power ratings not a bad option, and it does save us some money. If you go to the next slide, in the next slide, we first looked into the flux optimization, which is the figure on the left. You can see some bar graphs for 100% load down to 40% load, and you can see the total electrical power required to drive the system. The blue is the standard configuration as we found the test setup. In red, you can see the effect of the automatic field optimization, which is commercially available. And by manual adjustment, we end up with the green bar. You can see that even at 100% load and some manual tuning of the flux, we could already increase the system performance. And of course, that flux optimization becomes more interesting at lower load. So at 40.6% of load, you can see a bigger saving. Now, if we take the 100% load, to go back, thank you, yeah, and we look to the right graph, there we combined both the switching frequency and the optimization of the flux of the machine. So we started with the blue, which was the original setting of the system. Then we went to the red one with automatic field optimization. Green was the manual optimization, and then we also adapted the switching frequency. So, and then we end up with a reduction of, where did I wrote it down here? 4% of reduction in the energy consumption of this particular system, which is not bad, of course, because actually we did not change any hardware. We had no investments. We just had to know what to do with the parameters. And of course, we needed a measurement of the electrical input.
Now, given that information, allow me to offer you some practical guidelines, because I hope we have convinced you that simply tuning these parameters can already save you a little bit of energy. But of course, as was clear from the previous slide, it is case dependent, and it will always be case dependent. And so in that sense, a measurement campaign is a must. Thankfully, most power electronic converters today typically have a form of energy measurement or measurement built in. So you can typically use, if you have access to the software, the internal measurements of the drive. It will give you already some idea to perform a baseline calculation or a baseline measurement. Alternatively, of course, you can install a power analyzer on the AC in-feed, which does not require the stopping of your devices. Now, when you measured the baseline, then of course you can try to adapt the parameters, which is typically done in the drive software. So as presented, the automatic flux optimization is an option to enable, but manual flux can be better if you have a better sense what is actually required for your machine. Of course, you then can set the switching frequency, which is typically also only one parameter, and you can set the DC bus voltage set point for your active front end. But especially with the latter one, you should be careful with under or over voltage warnings. So these are potential limits to take into account, or warning thresholds to reprogram as well, if you have a proper understanding of what's done. Well, some advice that we can give is to also retune the automatic controllers if that's a requirement, or if it's a potential. So most of the drives today have some kind of automatic tuning built in for the internal PID controllers, for example, and those can be tuned after the adaptations which have been made. And of course, you should then measure again your results to confirm that you have indeed saved energy. As mentioned, it's about finding the optimum. And thereby we already reached the end of this session. So let me summarize the main conclusions. For flux control, we can save somewhere between 2 to 6%, particularly in part load, where you don't need your full torque dynamics. And overall, the lower the flux, the better, trading off with the torque. For the switching frequency, you have a potential to save up to 1% of energy, where 4 kilohertz is a good best practice. And for the DC bus voltage, worst to best is around 5% difference, and the optimum will depend on the power rating of your system. So in that sense, always consider the measurement. We gave some tips on practical implementations, but most importantly, always know that your drives are part of a system. So you should properly understand the system, know how your drive is part of that system, and you can achieve the best results. And with that, I can close the presentation part of this session and open the Q&A. But prior to really opening the Q&A, I would like to remind everybody, for those that didn't know yet, that Van der Smeek also has a podcast where there is a session now available online, also on energy saving, and there are many other very interesting topics on that podcast. And with that last statement, Seppe, you can take us through the Q&A.
Okay, thank you, Jeroen and Kurt, for the clear explanation. We have no questions so far, but as some people are watching this session with a delay, I suggest we wait 1 more minute to see if there are still questions coming up. Yes, we have first question. Can you accumulate the savings and save 11% of energy based on parameters?
Well, I think that's a little optimistic. It of course depends on your system, but I think that by just optimizing the parameters of your drive, as we showed in the case, we ended up with 4%. I don't think that 11% will be realistic. But as Jeroen said, typically if you have the time to analyze the entire system, starting from the actual work that needs to be done in your process, then of course by analyzing the whole system, you typically can end up near 10 or 11%. But by just adjusting the parameters of your drive, that's too optimistic.
Okay, thank you, Kurt. We have a second question. It's in Dutch, so I'll first read it in Dutch and then quickly try to translate it for people who are only English speaking. Als motor en drive samen overgedimensioneerd zijn ten opzichte van de pomp, zijn winsten dan ook daar te halen? So if the motor and drive together are overdimensioned regarding to the pump, are there also gains there or not?
Well, actually there are, because if it is oversized, then of course flux optimization is a useful tool to make some improvements. It also, it is already with a variable speed drive, so that's good because you don't burn your energy over a valve. So that's good because we still see a lot of applications in industry where valves are still used, but here it's not the case. But you have to be aware that if you go to part load, you will reduce the speed of your pump, so your pump will be more efficient. That's positive. But your motor drive system is still generating too many losses to be as required. So I think that flux optimization here would be a typical thing. Now it depends on the type of drive, because sometimes you have to program a voltage flux line, and in normal operation that voltage flux line is linear. But some drives, and all the drives had that on board, also had parabolic voltage over frequency lines, and that is similar to flux optimization. So if that's already implemented, then you're already doing a good job. I don't know, Jeroen, if you want to add something.
I believe that's indeed the best place to start. I think in general, finding the optimal set point of your motor, your drive, and your pump is going to be key here. To consider also the efficiency of the pump, because that's typically where even more losses are. So an understanding of the entire system, that's always the most profitable. And depending on your settings today, I think gains are for sure possible with the tips that have been given. So, but I would also start with the flux optimization. It seems the most suitable starting point.
Okay, thank you, Kurt and Jeroen. That was the last question, so I suggested there are no more questions. So I'll leave the floor to Jeroen to wrap up this session.
Well, thanks everybody for attending. The session is recorded, so if you want to have a look at the presentation again, feel free to go to our website. And then I have the honor of closing this 5-part series on energy reduction with these final words. So thank you very much for your attendance, and see you at the next occasion.